Hey folks, how's it going? So today we're going to be looking into designing a search autocomplete system. So this is a system that essentially enables you to get auto-completed search queries that you intended to search. Let's say you type Obama, then it's going to give you like a recommendation like Obama Nation, Obama Girl, Obama Biden, something like that. So this is pretty much based on some historical data, like previous search queries that people made. So the assumption is that you probably most likely to make that search query. So this is quite an interesting problem. So we're gonna try to design this because of we have to think about millions of users. You can think of Google search engine. It is millions of users, daily active users. So how do we scale to that number of users, right? And we're gonna approach this problem from a software engineering perspective. Then probably in the next video, we're gonna look into how we can solve the same problem, but from a machine learning perspective, and still pretty much achieve the same latency. So without wasting any time, let's get into it. So the first thing that we're gonna do is to narrow down the systems because this is a huge system. So the first question that we might want to know is that where is the matching gonna start, right? Like, is it gonna start when we start typing O, then we kind of like return the results, or at the middle of the sentence, or where does this the system has to kind of like be triggered as the user type? So in this case, we're just gonna assume that at the beginning of the search query. So that's where we can actually trigger the system so that it can give us the recommended search queries. Secondly, we might want to know what is the number of results that should be returned. We can say five recommended search queries. This is fine. Then another question one might ask is that um, how do we determine these search queries that we have to return? Like how do we know that we have to return these? Right. So they could be determined based on popularity, right? We could be having some sort of like a ranking system that rank these that rank which search query should be recommended to the user. Fourth, do we need to check spelling check? Do we need to check like spelling errors? Nope. The assumption here might be that we're gonna assume that the user knows what they want to search. So let's say someone search, oh, Obama. We're just gonna like make a recommendation based on what they type. So we're just gonna assume that they know what they want, right? Um, because of if we then start to correct because they are not done, right? Remember that they're still typing, they are not done typing. So we can correct what they are not done typing. So I think it's fine for us to assume that they have not made an error. So we're just gonna recommend based on what they have typed. So we don't have to like correct their mistake or something like that. So another question might be how many users do we have to serve this system, right? So we can assume 10 million daily active users, DAU. So that's the number of users that we can expect from the system. So we need to pretty much we have a lot of work to do because of if we have this amount of users, that means we need to build a very scalable system, which brings us to the requirement. So this system has to be fast, like way too fast. Have you ever went to Google and you kind of like type like a search query? You get those, um, you get those response like almost like instantly. So fast response time is gonna be a key element here. So we definitely need to be way too fast. So because of this requirement, that means that in our design, we have to like really think of things that are gonna make our system much faster. Um, because of obviously we want to be relevant because of we kind of like recommending these search queries to the user, so they have to be relevant based on what they already have typed. So relevant is going to be one of the key element in the system. Then we gotta look into also scalability. So scalability means that even if we have high traffic, right? Like there's so many users that are using our service. Like we said, that daily active users is 10, so the system should be able to handle this. Okay. Then we also need to make sure that the system is highly available, right? So so by highly available is that we do not want to see the system like being offline, right? No offline time. So this is going to be quite key because of all of these requirements. They're gonna essentially determine how we how we select certain component and for designing the system. So this what we are currently doing is quite important because there are certain systems well, components that you cannot choose because of you said that the system should be highly available. So what you are currently doing is very important as well. So anyway, uh, the result should be pretty much sorted because this can be sorted based on like I said, it could be some sort of like a ranking model, or it could be based on like their popularity. Okay, something like along those lines. Like let's say this the user says like Ronaldo. Maybe they search RO, then they get like Ronaldo. Maybe Ronaldo is like that's like the first search query because Ronaldo is like widely searched athlete or something like that. Maybe maybe they get something along the name that has RO or something like that. Maybe it's the second name or something like that. But the bottom line here is that the results will be sorted based on that popularity or some sort of like matrix that we're gonna get into. So this is our pretty much our requirements. So now let's kind of like estimate the kind of like amount of like requests that we're gonna be getting and the bandwidth and all of that so that we can be able to make informed decision as we select certain components across our system design. So every time when we try to estimate um, estimate the load of the system. So what do we need to think all the time, right? We need to think about the request, right? And we need to think about the storage. Um, we also need to think about the bandwidth, right? So we always all the time we're gonna be thinking along these lines, right? For instance, for the request, like we want to answer the question that okay, um what is the query per second, something like that, right? Like how many requests that the user going to make every second, right? So because of we said that we have 10 million uh, daily active users, right? That's the assumptions that we make, and we're going to make another assumption in that each user from that 10 million, each user make 10 uh, 10 search queries um, every day, right? So each user from that 10 million make 10 search queries on average. That's like the assumptions that we make. Now we're gonna need to understand the data portion, right? Um, so the bandwidth, in a sense, is that how can we do this? So we can assume that okay, from the search query, from that search box, right? Like when you type a word, let's say you type like hectare, right? We can assume that h like one character is equals to 1 byte. So one character is going to be equals to 1 byte. So what we're doing now is that we're trying to estimate the the size of this data, right? So we can assume that okay, one character is equals to 1 byte, but on average, how many characters or words do the user type? Right. So we can assume that okay, maybe the user type 4 words, right? So they type 4 words, and maybe those 4 words contains each word contain 5 characters, right? Which means that we're gonna have 20 bytes, so 20 characters. So which is 20 characters. Obviously, it's gonna be 20 bytes because we said that one character is equals to 1 byte, so it's fine. So this is 20 byte. So what does this mean? It means that for each query, this is the amount of data that we expect from each query. All right. So given that, for every character that is inserted within the search box, so if the user insert like something like H, we make the request to the backend. Does that make sense? So which means that if you're gonna say H, then we're gonna say search. We call this endpoint, which is gonna be query equals to H. Then you say you type E, then we make another query, which is search. Then we say query equals to HE. Then maybe search C, then make another search point. We hit the endpoint, so it's going to be query equals to HEC. So that's like the amount of requests that we're gonna make. So given that, how many requests to the backend for each query are we gonna make? So we're gonna be making 20, right? Does that make sense? Because we said that we have 20 characters. So you can think here it's gonna be T, O, we make a request. So we're gonna assume that for each query, we make 20 requests for each query that the user make. So this brings us now to estimate the request, like query per second. So what will our query per second be? So we said that okay, cool, we have 10 million users, right? Then we gonna multiply this by 10 queries. So each user make 10 queries a day, right? So we're gonna take 10 million by 10 queries. Then this is gonna be per day. And I'm gonna multiply this because of we said that each query it contain 20 characters. So it's gonna be times 20 characters. Then now we can take this to second because this is in day, right? So now we can take it to second. To take it to second, we're just gonna say 24 divide by 24 hours divide by 3.6 seconds. So this is gonna give us approximately around 24,000 queries per second. So this means that every second we're getting 24,000 queries. So every second, like 24,000 queries are made. So you can tell like the system has to be way too scalable. Then we can assume that the peak query, you always like multiply the query per second by 2, so that this is going to give you the peak query. So this is just to say that at the peak, like there's a certain time period within a day, like people search more. Maybe it could be maybe around 12 o'clock midday or something like that, because people maybe are busy at that time or something like that. So we're just going to multiply this by 2. So this enables us to kind of like um, cater for like peak periods, right? So yeah, that's that. So we're gonna have 48,000 query per second. Does that make sense? So remember that remember that the system has to capture data, right? Has to store data, right? Um, because of like remember that at the end of the day, let's say for instance, Ronaldo is scored a hat trick. Ronaldo is going to be trending, but we already have Ronaldo. We already have Ronaldo in our database. Like we're just going to assume that we already have stored Ronaldo. But let's say there's a new player that we don't know yet. Probably his name like is like Hector. He is a new player in the market. And people never searched for Hector. Let's just assume that it's a new name. So we need to store this because now we need to store that in our database, right? Because this is a new query, so that like we can calculate the popularity of this. Remember that we need to calculate all of those metrics, right? So we're gonna have to like compute their popularity and rank it. So, which means that we need to store data, but not all the data have to be stored because some of the data that the user search is already there. So, which means that we have to make another assumption. So, the assumption is that we're gonna assume that 20% of the queries that are being made, right? 20% of those, we're gonna assume that they actually are new queries. 20% of the queries are new. So, which means that we're gonna try to find the size of that of the size of the new queries that we need to store. What's the amount like, right? So given that we have 10 million, right, we just need to go back to the amount of like the queries that the user makes. So given that we have 10 million users and we know that each one of them makes 10 queries a day, right? So we can say that each query we know that it takes, what is it? We said 20 byte, right? So it takes 20 byte. So we're just gonna say I want 20% of this. I want 20% of this. So this is gonna give you 0.4 GB. So this is per day because we haven't converted this to seconds. So it's gonna be per day. So which means that every day we have to store 0.4 GB, right? 400 megabyte have to be stored in our database every day. So this is the new data that we kind of like expect. Okay. So this is our skill system. As you can see that it's quite heavy. So which means that we have a lot of work to do in order we can build a system that is going to support this. Now that we have estimated our load, let's try to propose some sort of like a high level design for our service. So you can think of a high level design. It's not necessarily a detailed explanation of each component, but rather some sort of like a starting point that we can both agree on, right? So it helps us to think deeply about the core functionality of our service. So firstly, we're gonna say that um, if we think deep about the service, it's just a query service at heart because the user makes a request, right? Based on the search term or a prefix, then the service is just going to return five most frequently searched terms, right? So that's that. Then secondly, at the heart of the service, we also have what we call data service because we know that if we get new search terms, we need to store those newly searched terms, right? So that's the core functionality of the service. So we're gonna get into like the nitty gritty of like frequency and all of that. But now, what is this data service? What is this data getting service? So we can think of it as like initially we have no query. Let's just assume that okay, we have this table and it has no query because of no user has searched. Then we have this frequency thing that we have here. Also, it is empty because no user has searched anything. But let's assume that we get the first user and there's a query, and probably they search something like Twitch. So this here is going to be now our table will be populated because we're going to have the query which is Twitch, then it's going to be one. So this frequency here, it's going to keep track of the frequency the query has been searched and the number of time it has been searched. Probably the second query, we can assume that it is going to be Twitter, something like this. Then we can also add it to our database. So firstly, we had Twitch, which is one. Now we have Twitter, and which is also going to be one. So this is something that this data gathering service it has to do. So its purpose is just have to keep track of the newly added search terms If the search term already exists, let's say someone search again for Twitter, it just has to increment the frequency, right? So that's like what the data gathering has to do. So let me just remind you, the reason we have a frequency is because remember that when we use this query service, we need to return we need to sort. Remember the requirement, right? We said that we need to sort them based on sort of like a frequency. So that's why the frequency within the data service is quite important. Okay. So now that we know that okay, we have some sort of like a table, and that table is storing our query as well as our frequency. So what will happen is that now coming to the query service, so what will happen is that this service its purpose just to return the five most frequently search queries. So we can assume that if the user types TW, because we stored Twitter and Twitch, and we saw that Twitter has like two. So what will happen is that Twitter will come first. So it will be like Twitter, right? Then it will be like Twitch, right? Something like this. Obviously, we're gonna return like five search terms, like so. So that's what this search query service is gonna do. So just to we can also write a simple SQL script. So we can say select all from frequency, or you can say select top five frequency table, right? When query like so you take the prefix that the user has searched. So if like they have searched TW, this TW will be here. Then you're just gonna have this percent. It's more like a regex. Just match everything before. That's what it means. Then you're gonna have order by frequency because we're looking for like the top, right? Then this is gonna be sorted in descending order. Then we can limit by five, right? Something along those lines. Then the query we it can return it can return those results. Like I said, what I came up with here is just like a high level design so that we kind of like understand the core functionality of this. But this is not necessarily an optimized solution. So we need to kind of like jump into like the detail of how this thing will scale to like what was it? It was 24,000 query per second. So how can we build something that can scale to that? So let's get into like the detail of the service. So coming to our deep dive, um, let me just choose a pen here, a color. Sorry about this. So coming to our deep dive, we need to optimize our high level architecture. Because our high level architecture is not necessarily optimized, it's just a way to kind of like give ourselves a direction and know what we should be focusing on. For instance, we can see that we were trying to use an SQL, but we're not going to be using a relational database because of then that means that we have to do the sorting on the on disk, which is going to be expensive. So we need to be thinking along the lines of in memory data structures, and this is where we're gonna need to talk about try data structure. So a try data structure, you can think of it as like a tree-like data structure whereby the root will always be empty, but uh, then the nodes can be hold the prefix, will be holding the prefix, right? And uh, at each node you can have for this node you can have like 26 children, right? Because um, there's like 26 characters, right? So for instance, let's make an example. Let's say you have a way like hecton. So the root is empty. Then we're gonna create a node which we're gonna store h, right? Then we go to the next character which is e. Then you store e here. Then you go to the next character c. Then you store c here. So you can think that if you get another name like Helton, right? So we already stored H, so we don't have to store that. Then we already stored E, so we need to store this new character, which is L. So we're just gonna create a node like so, right? That's like the basic concept of like a tree data structure. So let me just paste this image here so that you guys get to kind of like have a deep understanding based on Alex Yu book. So if we have let me just, I don't know why my pen get erased. Sorry about this. So we can think that if we have like a prefix like try, right? So what will happen is that we're gonna hit this T, then we're gonna go to tr, then we're gonna go to try. So this is like we find our match. So we need to store the prefix as well as the count, not necessarily the prefix, but should I say the search term query, the query itself. So um, if for instance, let's say you have like try, this is like the search query that the user hit, right? So you're not gonna like store the frequency here because of the way it is here. This is what you're looking for. That's where you're gonna store it. So check out my video if you want to understand the try data structure. I've already coded up solving a lead code question. I think it might give you a better intuition of how it actually worked. But anyway, the punchline is that we need to store the as much as we need to store the frequency alongside the search term, right? So now we're gonna have to analyze the time. I'm gonna get into like the detail of why this is quite important and why is it much more efficient. Just stick with me for now. So I wanna get into how will then this help us to then get to the bottom line of the question. I remember that we said, okay, given the prefix from the user, we want to return the top most frequent relevant queries, right? That's what we want to return. That's what we said we want to return. But then how will this data structure help us achieve that? So, and will it do it efficiently? So let's have some terms here so that we can be able to analyze also the term complexity. So let's assume that P is going to be the prefix length, right? This is going to be the prefix length, as well as we can have N, which is going to denote the total number of nodes, So this is what it will mean. Then we can have C. C is going to be the number of children at a given node. So number of children for specific node, right? So that's what it will mean. So now, how will this work? So the first thing that we need to do is that we need to find the prefix, right? Find the prefix. That's what we need to do. So how will this take? For instance, if we have like try, so we need to like traverse like tr, and try. So we know that okay, the term complexity of this is going to be O of n. So right. So now we find the prefix, but we also need to find the children because we're looking for the top five most relevant queries. So which means that we're gonna have to also traverse through. We're gonna have to traverse through the children, right? So this is gonna be O of C. So which is because of C is the number of children. So just to make an example, so if like you're at TR, you can think that you have to get all of these children. So we have a three here, that's the children. We have a true here, that's the children. We have a try here, that's the children. Does that make sense? I hope it does. So the term complexity will be O of C. Then coming to we are not done. We now have to get that top five. So we have all the children which are relevant based on the prefix, but now we need to get top five. So what do we do? Which means that we need to sort. So we need to sort and get that top K, right? That's what we need to do. So sorting algorithms, like the most efficient algorithms, whether it's quicksort, the term complexity for this is gonna be O C log C, because of we're gonna be sorting the children. So that's why I'm using C here. So you're gonna have to sort those children and then get the top five. So the punchline is this is like the term complexities of us actually getting um getting the top five most frequent stuff. But we need to then optimize this. We need to then think of a way in which we can make the service much more efficient. So what can we do? So in one way we can say, because now the goal is just we're reducing this time complexity, right? We're trying to make this much more efficient. Can we say that let's limit the what is it, the max length, of the prefix, right? Remember that we said that, okay, we have the prefix length here, right, which allows us to know how far we should traverse. But we can actually limit that. Maybe we can say, okay, you know what, we're gonna make it 10. So something like that. So now this allows us to say it moves us from OP, right, to constant. So it moves us to O of 1 because of 10 is constant, right? It's just one, it's constant. So this is much better complexity than O of P, because O of P can be large depending on the prefix of the user. So which means that O of 1 is much better. So what is another optimization that we can do? Another optimization that we can do is that we can actually cache, right, the top top searches. So and this is quite good, because imagine that all the time, even if like you already have search hector, right? We know the top the top search terms that were returned. Then somebody else search hector again. So we already have cached we already have those results returned. Why don't we then cache them here? So we need to find a way in which we can cache them. And this is one thing that we can do, is that we can cache these things within the tree itself, right? We can think that going back to a tree, we can say, okay, you know what? These guys here, just get my pen again. It always gets overwritten. Anyway, we can think at TR, we can cache these stuff here. We can have tree here start. We can have true start alongside with the frequency. We can have, and the good thing is that they are sorted, so which means that true is going to be number one here, which is 35. Then you're going to have try here, which is 29. Then you have tree. So you have like this. So the punchline is that now, when you get to try TR, you don't have to then go through and get all the children and do all of that heavy work and then come back and sort. No, you just hit this point and you just get it. So which means that this is going to be all of one operation. So we removing that we're removing the sorting as well as traversing through the children to get to the top 5k terms. So this is much more efficient. So those are the optimizations that we can make to make our this try data structure much more efficient. So now let's talk about our data gathering service. So this is the service that we spoke about in the high level design architecture. So now we just need to get into the detail of how this will work. So if you can remember, we said that the data gathering is that when the user essentially have a search, right, term or a prefix, right? They have a search term or prefix. We said that, okay, if it happens that this is new, we need to then go and update, because we know that we're using our try data structure. We need to go and update our try data structure, right? So you can imagine that we have to then insert that prefix, and also remember that we're not only catering the new term, but also we need to keep track of the frequency. For example, like I said, Ronaldo, we just need to make sure that we count that, right? Also, So which means that we need to like it's already a well-known name, but we need to count the frequency of how many times this has been said. Maybe this is trending or something. So we need to keep the frequency. So which means that we need to make the update to our try data structure. But the question that I have is that given given that we said that we have 24,000, right? We said that we have 24,000 queries per second. That's what we said, right? So every second, imagine that we have to then make updates to this try data structures. This is not efficient at all. It's just even not, I don't think this can actually work, right? Because now, like, you have to make the updates like in a second, like, it's just not going to cut it. So we need to come up with like an architecture that can work, right? So one way we can think about it, just to kind of like come up with a higher level architecture, so we can have analytical logs, right? We keep the logs because of, remember that when you make the updates to your try data structure, remember that obviously you're gonna affect also the queries that are coming in, so it's gonna slow down the service. So hence here I'm trying to decouple the updating portion from the so that like this can happen separately. So I'll show you what I mean. But anyway, let's assume that we have analytical lock. So this is much efficient to write to because it will be an append only, whereby each set each prefix that the user makes, it will be appended here. So we can think here we have Hilton, then we just gonna have time here. So right, we have time that okay, this was set at this time 2023, whatever, whatever. Then we have Hector, this was set at this, so this is just coming in, all the data is just coming in inside this. So this can be very large, but and the data might not be in the right format that we want, so which means that we need to then have some sort of like an aggregator. We do this, so we're gonna have aggregators, which I'll actually explain what they will be doing. Then this aggregator data, so essentially this aggregator data will be mainly focusing on making sure that they compute the frequency, right? So you can think, because of we said that this is append only log, so maybe at this time Hector was also assessed, so the aggregator service will be computing the frequency, and this will be more like something that we do in a weekly basis, right? Not necessarily we do this in a weekly basis, but we update our try data structure in a weekly basis. I'll get into that in a second, but I just wanted to make sure that you understand that these are going to be the aggregators for the frequency. Then the aggregated data will also be stored inside like a persistent database, right? Then we can also have the workers. So the workers are going to be responsible for creating the try, which they will update. So this will be a weekly thing. So this is going to be our try DB, try database. Like so, right? So this is the persistent try database. So it's not necessarily where we read from. So we need to read from the memory. So this is going to be the try cache. So this is just to say that if like our cache goes down, then we kind of like pull from the snapshot of this try DB. Then this is going to be our try cache. So this is the cache data inside here, right? So the the punchline is that the coming from here is that we're going to be aggregating this the frequencies of this, then we're going to store the frequencies um, of this prefixes, and we're going to store this inside the data. Then the workers will be able to will need to create the try data structure and store that inside the DB. So we're going to talk about how is that created. Then this is going to be a distributed cache that is stored in memory to kind of like save our request. So this is much better because as you can see that we are not all the rights like what the user type is not necessarily affecting our cache. So the queries are not necessarily affected here. So this is much better. And the thing is that we are making these updates weekly with the assumptions that the reason I said weekly, we're making the updates weekly is because the assumption might be that the search term do not change that much, right? Um, maybe you can discuss this. It might differ. Maybe the interviewer might say, but what if there's a trend going on and something like that? So it differs on specific UK. So yeah, it's different for everything. Anyway, so how does this work then? The workers, how do they then create that try data structure? So the workers are building the try, but also after they have built the try, what they need to do then is that they need to persist that data as shown in our architecture, right? So that's the first step. But then how do they persist that data? Because of the idea is that how will they then store this tree that we spoke about, right? They can use a key value store to store. They can store the try that they have constructed in a key value store, right? So the idea here will be that the key essentially will be the prefix, right? And then the value here will then be the nodes that we said that we're gonna cache. You still remember that when we said that, okay, at each node you can cache like the top five, right? So for instance, like B, maybe this was searched, like maybe let's say the prefix is B, then you have BE, and this was searched maybe 50 times, maybe you have a B, which this was shared 80 times and so on. So you have top five of these, and this is more like a hash map. So you have the key as well as you have the value. So you construct this and you store it inside this try DB. Then every weekly, what it will happen is that then there's going to be a snapshot that is sent inside this cache. So this cache will be updated on a weekly basis. The reason I said weekly is because of the assumption is that we assume that the search term do not change that frequently. So maybe we can have like data scientists to kind of like validate that assumption for us to search if like to show us like if like that's actually the case because of if you think about it, maybe the interviewer might say, yeah, but what if we have like trends going on like for today and something like that, so we want to capture that, we want to capture that, so this might change or something, but it wouldn't change that much, but that's the idea. There is another option you can use, but I'm not gonna get into, which is instead of using a key value store, you can also use a document store, which is something like MongoDB. It's one way you can. It's another thing that you can use. But anyway, now we spoke about the data gathering service, but there's another service that we haven't touched, and we spoke about in our high level architecture, which is the query service. So we need to go deep into this as well. So the query server is going to be the one that is responsible for querying that try data structure that we spoke about from the cache and returning the results to the user. So how does this look like? So we can imagine that we have our UI whereby we have the user, right? And this can be from the web or mobile, right? So we can have a load balancer. We can have a load balancer. So the idea here will be that the load balancer will distribute the request to like API servers, right? API servers. So you can think here we have these API servers which are horizontally scaled, and then these API servers will then hit our try cache that we spoke about now from the data gathering service. So this is going to be our try cache. Then this try cache is constructed from getting snapshot from the try database, like so, right? So this is pretty much our high level overview. So a search query, like you can imagine that we have a search query from the UI. So the search query is gonna come to the load balancer. Then the load balancer is gonna route that request to the API server. Then the API server is gonna be responsible from constructing the autocomplete suggestion for the client by getting the data from the try cache. And it could be happening that the search query that the user have sent to us, it's not necessary in the cache. We can actually go and get that from the try database, and then we can actually cache it. So that's one thing we can do. I think this is what we call read through cache. Anyway, like I said, we need to make this guy to be way too fast. So the query service has to be fast, right? So what are some of the optimizations that we can do to make this query service fast? So one way is that we can have Ajax request. So the idea behind Ajax request is that sending and receiving a request response does not refresh the whole entire page. So right, Ajax request does not refresh entire page, which is pretty cool, right? Um, Through we can have browser caching. So some of the search queries that the user has made, we can cache them on the browser. So we do not have to then hit the services that we have from our server. So the user can get this from the browser. So this is way too fast because it's right next to the user. Okay, looking into our system, let's try to log into our try operation, right? So we kind of like spoke about the creation. So we know that okay, for us to create a try, this will be created by uh, try workers. So they will be the responsible for getting the data from the aggregated data because that's where it starts. And then you use that data to create a try. Then you store that, you persist that in a database. We said we're gonna use a key value store table. That's where we're gonna do that. So then the update. Then we said that we're gonna update our try that is inside the cache. We're gonna then do that in a weekly basis. So we're gonna get the snapshot from the persisted try. So like I said, these workers are gonna store this in the database, which is gonna be persisted. Then we need to update our cache, right? So that's where that we're gonna do this process on a weekly basis. So that's what I meant. So that's that. Then what's next? We can talk about the deletion as well. Um, so one thing that we need to talk about is the words which are harmful. I don't know if that's the right word, but the words which are not accepted, like right. So if we have our API server here, there are certain words that we want to filter from the try cache. So if we have our try cache here, and we can have a filter layer, right? So this is to say that we we do not want to suggest these words to the user, right? Something like, maybe let's say the user type dr, then you don't want to like suggest drugs or something like that. I don't know, maybe I don't know, maybe Google does. I'm not sure, but the punchline is that maybe you don't want to suggest something like that, right? So you have this filter layer that is gonna do that for you. Or maybe you can actually, even if like, so that you don't like slow down the you don't slow down the query process, because that is quite sensitive in terms of latency. Maybe you can do this as you constructing the try, because of when you construct the try, because we do this weekly, so it's fine if we take time. So as you construct the try, you just make sure that there's certain weights that you don't want to store, like right inside the try. I don't know, maybe that's like another way we can think about it. So instead of storing the filter like on the query service, because of this is sensitive um in terms of latency. So we said that, okay, our cache, right? Our cache can't store all the words in the world. Like, right, there's a specific number of size that it can store. So, which means that this thing here has to be distributed. So, our it's gonna be a distributed cache. So, which means that our data will be stored on different nodes, right? It will be stored on different nodes. So the question now becomes, if our data is being sharded on different node, then let's say here we have like specific weights, then how would we know that we have to get like data from this shard? How would we know that? So which means that we need to know about sharding techniques that we're gonna use to kind of like get the data from a specific shard. So one way we can shard this data is probably by characters. So we can say that, you know what, um, because I remember that you are passing the prefix, right, to the service. Then the service has to return the top five, right, the top five relevant search queries to you, right? So if you search a prefix, maybe let's say the prefix is h, then based on this, we can go to specific shard. Let's say all the words that have H are in the shard, are in this shard here. H, all the all the all the all the prefixes are gonna be inside here. So we can then return all the data to you. So we can do something like this, meaning that all the shard is gonna store. We can shard based on the alphabets, right, from A to Z. Maybe we don't have enough like nodes. Maybe we can choose specific. Maybe we can have a range to say that A to M is gonna be inside this. Maybe um, then maybe from like Y to Z is gonna be inside this shard. Maybe like something like that. So we can do something like that. But the problem with this sharding strategy that you might have realized is that if you have like a shard from probably W to Z. So like this node will never be utilized because there isn't too much words that people search within that have start with these weights, right? So so then you're gonna have an equal distribution of like nodes usage. So you don't want something like that. You want all the nodes to be used to probably the same way, right? So one way we can think about this is probably to have what is it? A short map manager. So the idea is that this just kind of like throw it again. So if we have our web API servers here, um, right? So it's because we need to retrieve the data from the cache, so we know that this cache data is sharded, right, based on specific characters. So instead of saying A to like C, F to, or instead of doing this way, what we can do is that we can have this shard manager. So the idea here is that the shard manager, it's gonna do some sort of like analytics whereby it says that, oh, S actually has the same number of queries with the characters from Y to Z, maybe something like that. So S is something like that. So the number of queries that S has is similar to these combined. Maybe also you can include Excel, right? So which means that then you can say that S is gonna be starting. It's gonna have its own shard. Then X, Y, Z is gonna have its own shard. So that's one way you can do. So the idea is that because of they have the same like number of queries, so you can as well do that, right? So that's a smart way, yeah, in order we can evenly distribute the request to different shards. So yeah, but yeah, that's the try and system design for designing a system that can do what we call autocomplete. I have to say that I will do probably a second video on like how we can build the same system but using the machine learning, and we can see if we can be able to achieve the same pretty much latency using machine learning algorithms, and how we kind of like go from software engineering, we jump into machine learning, and we think more like machine learning engineers. So thank you guys for watching to the end, and I'll see you guys in the next one. Thanks, bye.